Hi everyone. So far we have seen control rectifier drives. So where AC supply is available, we need to convert into the DC to use it for the DC drives. So this is another type of converters, that is where the DC supply is available. If you want to use it the DC supply for the DC drives, we need to use the DC to DC converters. So the DC to DC converters have, or DC drives have the advantages like it will give the high efficiency and very flexible in control, and very few switches will be there while operating, and it is because of that it is lightweight. Actually the converters are lightweight, hence the drive weight will be light. That's why it is in smaller in size. It will give the quick response. So all these are the advantages of the DC drives. Even the regeneration also, it can be done at very low speeds also. So all these are the advantages of the DC drives. So the applications like interactions or servos or lifts, trolleys. So all these are the applications of these DC chopper drives. So anyway, we'll see one by one the DC controlled chopper drives. Here the first one is chopper control of DC drives. In that we'll see the motoring operation of separately excited DC motor. So here we'll see the motoring operation of the separately excited DC motor. To get the motoring operation for the separately excited DC motor, the power circuit diagram is shown here. The supply voltage is connected through the switch to the DC motor, and across the DC motor diode is connected. Diode is connected across the motor, and the corresponding output voltage is VA is equal to V0, and corresponding output current is armature current. The motor equivalent is nothing but RA, LA and E, that is equal to the motor equivalent. It looks like step down or buck converter, and it is called the step down chopper or type A chopper. Type A chopper or buck converter. So where you are getting the bucking operation, that is called the type A chopper. So coming to the operation of this drive. So as this is single quadrant converter, we'll get the single quadrant operation by using this power circuit diagram, because our aim is to get the motoring operation only here. To get that motoring operation, only switch S is there, or switch S1. So that S switch need to be operated. It need to be operated means we need to turn on and turn off. While turning on and while turning off, what are the operations it took place, that we'll see. When the switch S is operated, only one controlling switch, that is S, and the other switch is diode, that is uncontrolled switch. That's why switch S we are turning on and turning off. Okay, when the switch S is on, the diode D is in reverse bias, because positive supply is connected across the diode, cathode and anode. Hence it is in reverse bias. When switch S is on, the current will flow through the motor, that is nothing but motor inductor. So inductor LA will get energizes during the switch S is on. During that time diode D is off, that is called the power mode. When the switch S is on, the entire source voltage is applying or appearing across the motor. Hence VA is equal to V. So VA is equal to V is equal to, if we apply the KVL to this outer loop, we'll get this equation. VA is equal, which is equal to supply voltage, which is equal to the RA into IA plus LA into DIA by dt plus E. So the next case, when the switch S is off, earlier during the power mode, the inductor stores its energy in the energy stored in the inductor. The inductor is energizes. The inductor need to discharge or de-energize in the same path, because inductor doesn't allow the sudden change in current. It do not get reverse its current. So it need to allow the current in the same direction. To allow the inductor current in the same direction, as switch S is open or switch S is off, this is close open path, only diode D need to conduct, because for this inductor current diode D is in forward bias, so it will free wheels through this diode in this direction. So diode D will be getting in this loop. So the stored energy in the inductor de-energizes through this diode D. Hence the voltage across the motor load, because diode D is energized or diode D is in conduction, means simply short circuit across the motor load, hence the VA equal to 0. VA is equal to 0 is equal to, again we are applying the KVL across this freewheeling loop. So VA is equal to 0 is equal to RA into IA plus LA into DIA by dt plus E. That is the equation. By using these conditions, if we draw the circuit diagram, Vs is nothing but source voltage, where it is constant voltage V source voltage. If we see the output voltage waveform equation, output voltage and current, that is nothing but VA and IA equations. During the switch is on, let us assume this is the turn on period, this is turn off period, this is total time period. During the switch is turn on, when the switch is on, your VA equal to, or output voltage equal to supply voltage. That's why during the turn on period it is equal to the supply voltage, VA is equal to V here. And during the turn on period, the inductor stores its energy and it energizes. It is charging, right? So inductor is in charging mode or energizing mode. Next, when the switch is off, inductor need to discharge its energy through the freewheeling diode. Hence, the voltage across this motor is equal to 0, because simply it is getting short circuit. That's why the voltage equal to 0 and inductor need to discharge its energy. That's why the inductor current is decreasing. Again we are turning on the switch, voltage will be appeared across that, inductor stores its energy, it will be continued, right? So in this way we will get the output voltage. When the switch is on, output voltage is appeared as source voltage, and when switch is off, it is equal to 0. Inductor current will get charged and discharged during the on and off times. So by observing these waveforms, your output voltage is, or armature voltage is always positive with the positive current only. That means it will be the quadrant 1 operation only with this power circuit diagram. So here if we see the duty ratio D or del is equal to, duty ratio is nothing but turn on period by total time period. So T on by T is nothing but duty ratio. And if we apply the Fourier transform for this output voltage, if you want to find out the average voltage for this waveform, average voltage VA is equal, V0 is equal 1 by T integral 0 to T turn on time, 0 to T and V of T into dt. Here 0 to T can be split into the 0 to T on plus T on to T off. T on to T off, anyway the voltage equal to 0, that's why only 0 to T on is considered, VA into dt. So if we apply this integration, T on by T into V, because VA is equal V during the turn on time and T on minus 0 by total time T. With that, T on by T is nothing but duty ratio del, so VA is equal del into V. This is the equation. VA armature voltage as a function of duty ratio del, this is the equation. Now we need to substitute this equation in the speed equation, like earlier fully controlled rectifier, what we have seen. First power circuit diagram, the corresponding voltage equations, and then we can find out we can use the equations to find out this VA equation as a controlling angle. Here controlling angle is nothing but delta. So del. So power circuit diagram, voltage equations, power circuit diagram is used to draw these waveforms. These waveforms are used to know these equations. By getting these equations, VA is equal to del into V, we can substitute that equation in the speed equation to draw the speed torque characteristics. Now what is the speed equation? Omega m is equal to E by K pi. E is nothing but VA minus IA RA by K pi. So VA by K pi minus IA RA by K pi. So VA can be replaced with del V by K pi minus RA by K pi square into T, where T is equal to K pi into IA, because IA can be replaced by T by K pi. Hence your equation will be like this. So if you draw the speed torque characteristics for this drive, where you are getting only single quadrant operation, that is both positive voltage and positive current, that will give the forward motoring mode. Only forward motoring mode. In this forward motoring mode, the speed torque characteristics as speed is directly proportional to the controlling angle. As controlling angle is decreasing, del 1 is greater than del 2 is greater than del 3, your characteristics, speed torque characteristics will shift downward like this. So here del is decreasing. As del is decreasing, for first value of del, you may get the characteristics like this. Then the next value of del, if it is del 2 is less than del 1, then the characteristics will be shift downward than the del 1 characteristics. In this way, in the single quadrant, you will get the speed torque characteristics for this separately excited DC motor. Even if it is equally applied for the series motor also, simply series motor means you will get the characteristics like this. Like this. Speed versus torque. And the controlling angle del decreases like this. So in this way, and this is for series motor. So this is for separately excited DC motor, and in this way we will get the forward motoring operation. To get the braking mode or to get the regenerative braking mode, we need to change the power circuit diagram a little bit. We need to change the power circuit diagram. The changes are like this. Earlier in the forward motoring mode, the switch and diodes are placed. Diode is placed across the switch, diode is placed across the motor, and switch is in series with the supply. Now we need to interchange both of them. That is, now diode is coming in series with the supply and switch is across the motor. Okay, if we see here, when we are keeping the power circuit diagram like this, again here, as this is also single quadrant mode, because we are aiming at only regenerative braking mode. That's why regenerative braking mode, forward regenerative braking mode, it is in the second quadrant. As this is single quadrant converter, we used only one controlling switch. So here, how many controlling switches are there? That many quadrants you will get this operation. So in this DC drives, if you are using the two controlling switches, there is a possibility to get the two quadrant mode. If you are using four quadrant switch, four controlling switches, you will get the four quadrant converter. Okay. So here again the switch S is operated. S is operated means we need to turn on the switch and turn off the switch. While turning on and turning off, what are the operations? Turning on means the operation is in between the 0 to T on. Your time between the 0 to T on, or 0 is less than or equal to T is less than or equal to T on. What will happen when the switch S is on? When the switch S is on, as this is braking mode, regenerative braking mode, the back EMF will work like a source, and the stored energy, the generated energy in the load is transferring towards the source side. So when the back EMF is act like a source, the IA current will flow in the opposite direction to the assumed direction. Earlier in the motoring mode, IA is in this direction. Now that is in the braking mode, it is opposite to the earlier current direction. So IA current is flowing in the reverse direction when the switch S is operated. When the switch S is on, the switch S is on means it will short circuit the motor. So VA equal to 0. During that time, this back EMF will energize the inductor. That's why this is energy storage interval. Now LA is charging. When the switch S is off, now the time is between the T on is less than or equal to T is less than or equal to T. This is off time, switch off time. During the switch off time, simply the stored energy in the inductor need to discharge in the same path, in the same direction. So that makes the diode D into the forward bias. Hence, the outer loop will come into the picture. When we apply the KVL across the outer loop, the corresponding armature voltage VA is equal to the V, right? So VA is equal to V. And we need to remember one thing here, it is IA is negative in the regenerative braking mode. It is opposite to the earlier conventional direction, and the switching off period is called the duty interval. And if you see here the corresponding voltage waveforms, so source voltage is constant. If you see the output voltage is here the power circuit diagram. When the switch S is on, the output voltage equal to 0. When the switch S is on, the output voltage is 0. When the switch S is off, VA equal to V. It is equal to the supply voltage. When the switch S is on, the inductor is charging. That's why the current is increasing. When the switch S is off, the stored energy in the inductor will discharge through this diode, right? So that's why it is decreasing. Inductor current is decreasing or armature current is decreasing. So in this way, it will be continued for the rest of the cycle. So here duty ratio del is called T off by total time. During the turn off time, you are getting the output voltage. That's why that is called the duty interval. T off by T is nothing but total time minus turn on time is nothing but T off. So total T minus T on by T or T off by T is called the duty interval by total time. Okay, now del is nothing but T off by T. So or T minus T on by T. For these waveforms, if we want to find out the average voltage, so VA is equal 1 by T integral T on to T, because 0 to T on, your voltage is 0. Hence, we are using only T on to T, which is equal V into dt. So V into T minus T on by simplifying this one will get the V into T minus T on by T. That will give the VA is equal del into V, because T minus T on by T is nothing but del. So now here also we got VA is equal del into V, but here del is nothing but T minus T on by T. Earlier T on by T only. So now if you see the basic equation like VA is equal in motoring mode, VA is equal E plus IA into RA. But because of the armature current is negative, it will become VA is equal E minus IA into RA. So that makes the E is equal VA plus IA into RA. As we got this VA equation as a function of controlling angle or controlling delta, so you can use the same equation in the speed equation. Speed omega m is equal E by K pi, which is equal to E is equal to VA plus IA RA by K pi. So here VA is equal del V by K pi minus RA by K pi square into T. By substituting this, IA is equal T by minus K pi, because IA is negative here. So again we'll get del V by K pi minus RA by K pi square into T is the speed equation. So by using this speed equation, we can draw the speed torque characteristics. The speed torque characteristics are like this. Simply the motoring characteristics in the first quadrant will be extended into the second quadrant to get the forward regenerative braking characteristics. Earlier these are the forward motoring characteristics, right? That will be extended onto the second quadrant to get the regenerative braking characteristics. So this is forward motoring, this is forward regenerative braking characteristics. Here one thing we need to remember, that your source is nothing but, your motor side is nothing but source. That's why in regenerative braking mode, your E should be greater than this V. To make that E should be greater than V, we need to control this del. So E should be greater than del V, then only your current will be negative. Because what is current here? Here if you see the current, IA is equal to E minus VA by RA. From here, your IA is equal to E minus VA. VA is nothing but del V by RA. So we need to make E should be greater than del V to get the regenerative braking operation. After IA becomes negative, I am writing this equation. That's why you are getting E minus del V by RA. So you need to bring this E should be greater than del V, then only the power will be transferred from this side to this side, from motor side to source side. So to bring that E should be greater than del V, here del is controlled parameter. By controlling this del, we can get this condition like E is greater than del V. Okay. So here also when we are decreasing the controlling angle, that is del, you can get your characteristics are shifting downward. Your braking characteristics also shifting downward for del 1, del 2, del 3 for the condition like del 1 is greater than del 2 is greater than del 3. Okay, this is all about the forward motoring mode and regenerative braking mode of the chopper controlled DC drives for the separately excited DC motor. Thank you all.